Okay, so today we are going to talk about sections 10.6 on alternating series and then 10.7 on root ratio tests. Root ratio test, of course, was included in the last section's homework, but I changed it because some of the problems asked you to use stuff from alternating series test, so we changed it to today. So 10.6, 10.7 are due today. So any questions on 10.6 or 10.7? Yeah.
Number 29.
On which one?
10.6.
10.6, number 29. Okay. Let me see. Yes. Okay. So we've got 20. This is 10.6. And we have the sum, k going from 1 to infinity, of negative 1 to the k, divided by k to the fourth. And they say n equals 4. So, okay, the directions for each of the following convergent alternating series: evaluate the nth partial sum for the given value of n. Then use the theorem to find an upper bound for the error using the nth partial sum to estimate the value of the series. Okay. So what they're saying is, okay, so if we went out 4 terms here, let's see what we get, and then we can estimate the error or how far we are away from the actual answer using the next term. Okay, so one thing that's kind of cool about partial sums, and I probably talked about this in the lecture, but it's worth saying one more time, is that what happens with alternating series like this is you start at 0, you move forward, you move backwards. You move forward, you move backwards, and you start kind of like honing in on some point, which is your answer. But what's cool about this is when you move the first time up here, then you move, let's see, I don't know how I drew this, but it wasn't perfect. Let's say that's 0. You move forward, then you move backwards, then you move forward, then you move backwards. So you're always the answer. Let's say this is getting close to, maybe the answer's right here. This is better drawn. So let's say this is your answer. You're always within one term of the answer, the next term. So if you've gone 3 steps, 1, 2, 3, and you're sitting right here, you're within the 4th step of the answer. And if you go 4, 1, 2, 3, 4, you're within the 5th step of the answer. Does that make sense? So you're always within the next step. Okay, using that, let's do this problem. It says find S sub 4. Right, so add up the first 4 terms of this series. So if k was 1, we would get negative 1 over 1, correct? If n is 2, I get positive 1 over 2 to the 4th. Is it 16? So next one's negative 1 over what? 3 to the 4th, which is 91. 81? 91. 81, right? And then what would be the next one? Plus 1 over 4 to the 4th. What's 4 to the 4th? 256? Yeah. So 256. Okay. So we've got 1, 2, 3, 4. So this is n sub 4. And then the question is, and then we could add that up if we want to. And if you wanted to use a calculator to do such a thing, you could, or you could get a common denominator. That's pretty horrible, but it could be done. Okay? So you get something. Then the question is, how close are we to the answer? The actual answer of the entire sum? Well, we know we're within the next term. What is the next term? Well, the next term, or I'll just call this the error right now, is the next term is 1 over 5 to the 4th. So that's 25 times 25, or 625. So we're within, I put a negative on this, but what do I mean by that negative? It means that it's behind us. So when we add this up, we get a number, and I'm within this amount of the actual number. So if I go back that far, I passed it. So if you wanted to get like a boundary for the answer, the boundary would be between this number and this number minus 1 over 625. And that would give you a boundary for the actual answer. It's not perfect, but it's an estimate, and sometimes it's good enough. The reason that this could come up is, like, let's say that you needed to sum up an infinite series like this. For some reason, some application came up and you need to sum an infinite series, but the best that you can measure is to like 4 decimal places. Like, you can't measure any finer than that anyway. So it's kind of like, okay, then how many terms do I need to go in this in order to get 4 digits of accuracy? And then don't worry about it anymore. Because why add up infinitely many things when I could add up 6 and get the same answer? Does that make sense to everybody? So sometimes when you know your margin of error of your measuring instrument, you can use that to say, how far out do I need to add in order to get a level of accuracy that is the best I could do anyway? So you may not have to add up the infinite series. You might only have to add up a finite number. So did I answer this question? You asked the question, right? Do you feel like you have what you need?
I think so.
Okay, do you understand? So I didn't actually do the calculation, but what is this? Do you have this?
Yeah, it's negative 0.9459.
Negative 0.9459?
Yeah, this is just it.
Oh, yeah. Okay, so there's this, and then this guy, if you were to put this into a decimal, would be what?
0.0016.
0.0016. So I can tell you that, like, the answer is this. Well, oh, this is, I guess in this case I have a negative, but if we think of it as error, it's this. And so I know that my true answer is between this and, okay, let me just write this one. Negative 0.9459 minus 0.0016. That's lower than my actual answer. And my actual answer is lower than negative 0.9459. So I know that I have a boundary for my answer between these two numbers.
Okay.
So this is the error. And I don't, usually when you have an error value, you take the error value on both sides, not just on one side like I did, but I know it's on that side because the last term was positive. So I know the next one's going back. Does that make sense to everybody? Other questions? Yeah. 10.7, number 17. Sure. Okay, so ratio and root test. Okay. So 10.7. This is number 17. And we have the sum k going from 1 to infinity. Of negative 7 to the k divided by k squared. Okay, and so the question is, they say use ratio test or root test. I can do what I want to here. I think that both ratio and root test could get the job done here. The reason that it kind of tells me to do a root test is I have something raised to the k power, and that's usually pretty good for the root test. The ratio test, I have like this k squared, which maybe it would be helpful to use ratio test, but I think in this case, let's try a root test and see how it goes. So what the root test tells me to do is let's take the limit as k goes to infinity of the kth root of this guy without the summation. So take the kth root of -7 to the k divided by k squared. All right, if I do that, I get limit as k goes to infinity. On top, I just get the kth root of -7 to the k, which is what?
7. -7.
It's kind of interesting, actually, like if k is a positive number, what do I get? So, oh, I'm sorry, k is always a positive number. Man, my mind is thinking right, my words are coming out wrong. What if k is even?
Oh, then positive 7.
Yeah, it would be positive because the kth root of a positive number is positive. What if k is a negative number? What am I saying? Wow. What if k is an odd number?
Negative.
Yeah, if k is odd, then this is an odd number, and the kth root of that odd number will be odd. So this is kind of interesting because it's bouncing back and forth to even and odd, which should maybe be a little bit of a warning sign. But let's just say for now, this isn't totally right, but I'll say it's -7. It depends if it's positive or negative. Is it -7? Is it +7? It depends. But let's just leave it as -7 for right now. And on the bottom, I have the kth root of k squared. Correct? And this is kind of like plus or minus 7 on top, depending on even or odd of k. Okay. So then let's just kind of look at what's going on the bottom, though, because it might help us out. So what's the kth root of k squared? Well, there's another way that I could write that. I'm just going to write plus or minus 7 on top for now. But I could write this as the kth root of k quantity squared. Correct? And does everybody remember in one of my lectures I said there are these 6 limits that you maybe would need to know? Yeah.
Doesn't that equal 1?
Yeah, equals 1. That's right. So we need to know that the limit as k goes to infinity of the kth root of k is 1. Yeah.
Do you know where we can find the 6 limits thing that we should know? Or I think it's in one of the lectures, but I don't
It's in the lecture. I think it's also in the book. Let me see if I can find that really quick. Sequences. Yeah, I think it's in the book as well. So let me find it really quick. Where is it? I don't see, I'll find it in a minute. I don't want to waste more time on it, but yeah, it is in that lecture. And then I'm pretty sure it's in the book too, but I just need to take a second and find it. I will right after class. But limit as k goes to infinity of k through root of k is 1. So this ends up being basically 7 if k is even, and it's -7 if k is odd. That's not good, right? It's oscillating between +7 and -7. So this limit as is diverges. So it's kind of like, okay, so that didn't work. So that tells me that, well, maybe we should look at the ratio test for this. 1 second. I think it's all okay, but yeah, it is okay. Okay, let me take a look at this problem one more time. So this is number 17. Yeah. Oh, because it's okay. Converge absolutely. So I was testing it with the negatives in, correct? So the negatives were in, and that's actually causing me problems. But what I probably should have done first is I should have tested it for absolute convergence. Okay, if I test this thing for absolute convergence, so instead of testing what I just did right here, if I put basically said, well, just make that positive, then this is positive and the negative basically doesn't matter anymore. So it's just +7 on top. And then when I take the limit as k goes to infinity, the bottom is 1 and the top is 7. What does that mean in a root test to get a 7 out? It diverges. So since it diverges, that means that this guy diverges, the sum of the absolute value. So that means that this one doesn't converge absolutely. That doesn't mean that it doesn't converge. But now that I know that it doesn't converge absolutely, I could use something like the alternating series test on it to see, does this thing converge or diverge when it has the negative in there? Question or?
Kind of, yeah. So the question asks if it converges absolutely or diverges. So like even if we do like conditional and we get like let's say we did the conditional and does converge conditionally, how would you get that there?
Yeah, that's a really, it seems to me like that's a typo, because I don't think they want to ask you if it converges absolutely or diverges. There is the possibility that it could converge conditionally. Yeah.
I feel like it's not a typo because like the next section adds the convergence conditional.
Yeah, it could be. You may be right. That's a horrible thing if they did it that way. They should be asking, does it converge absolutely, converge conditionally, or diverge? Because those are kind of the three things that could happen. If it just doesn't make any sense not to ask that question. So I think we should assume that they did mean to say converge conditionally. And so then we would test what's the limit as k goes to infinity of just whatever's right here, -7 to the k divided by k squared. And what do we think of this? Thoughts? It's certainly infinity over infinity. So I guess I could use L'Hopital's rule. But what do we think of what's happening on top compared to what's happening on the bottom? It seems like the top is getting bigger faster to me. One other thing to note is that now if this goes to 0, that's okay. If it doesn't go to 0, it's not okay. So let's go ahead and try L'Hopital's rule and see what happens. So we get limit, k goes to infinity. Can we even use L'Hopital's rule here? what would we get? Think about that for a second. How do I want to deal with L'Hopital's rule here? Obviously, the bottom is easy. What would the top typically give you?
Isn't it negative 17K ln 7?
Yeah, it would be ln negative 7, which is sort of not so great,
Yeah.
correct? You can't have ln of negative 7. And the problem here is this is kind of a weird function. Negative 7 to the k, because when k changes to the next thing, it changes the sign. Right? So, okay, I just am like kind of forgetting things today. I don't know. It's not even Friday, and I'm forgetting things. I don't want the negative in. So in the alternating series test, I don't need the negative. I keep putting it in. I did it before too, and it's making me mad at myself. So now if I don't need that in, now everything's fine. And I can take the derivative of the top and bottom. The derivative of the top is 7 to the k times ln of 7. The derivative of the bottom is 2k. I'm still getting infinity over infinity, so I could do it again, and I get the limit. As k goes to infinity of the derivative of the top now is 7 to the k times ln of 7 quantity squared. The bottom is just 2. And now what do I get if k goes to infinity? Well, 7 to the infinity is still infinity, and everything else is just a constant, so I get infinity. And infinity is notably not 0, right? So this thing clearly diverges. Okay, so therefore, I can say that the sum, k going from 1 to infinity, of negative 7 to the k, divided by k squared, diverges by the divergence test. And we're done. Okay, I apologize for that. I don't know why I kept on wanting to put that negative in there. So when we do a ratio or root test, we get rid of the negative before we do it, because we want to find absolute convergence in that case. We don't leave the negative in. Same thing with the alternating series test or the divergence test. We don't put in the negative, or else it kind of could make it sort of impossible, which it was making it impossible for us there. So make sure to get the negative out. And then once we did, everything was fine. Other questions? Yeah.
Can we do 22 on 10.7?
Yeah.
I just wanted to-
22, okay. Yeah.
We don't have to do 22. It's clause.
Oh, we don't.
My mistake. 21.
Oh, 21. Yeah. So 21, we have the sum k going from 1 to infinity of k factorial quantity squared divided by 2k quantity factorial. Now, the one thing that is nice about this problem is it has factorials. And whenever you see a factorial, it should basically be screaming at you, please use the ratio test. The ratio test works wonderfully with factorial. So let's go ahead and do it. Okay, so what we want to do is we want to take the limit as k goes to infinity. And we want to put the k plus first term in up on top, and we want the kth term down on bottom. So we take the k plus first term would look like k plus 1 factorial quantity squared divided by 2 times k plus 1 quantity factorial divided by k factorial squared over 2k quantity factorial. Okay, so we've got a fraction divided by a fraction, so I could flip and multiply. So let's do that, and I get the limit as k goes to infinity of k plus 1 factorial squared, right? But just for the sake of right now, since it's squared, it means just multiply it by another one. So I'll just say k plus 1 factorial. So I've got k plus 1 factorial times k plus 1 factorial. And then on the bottom, I have 2 times k plus 1 quantity factorial. So 2 times k plus 1, another way of writing that is 2k plus 2. And I think that that will be helpful to us. So I'm going to write 2k plus 2 quantity factorial. Then I'll flip and multiply the bottom. And so the 2k factorial goes on top. So I get 2k quantity factorial. And on the bottom, I have k factorial times k factorial. K factorial times k factorial. Okay, and now we're ready to do some cancellation. Now, everybody remembers sort of what this means, right? Okay, what k plus 1 factorial means, this is equal to k plus 1 times k minus 1 times and so on times 3 times 2 times 1. In other words, like 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. Right? It's just like take that number and multiply it by every positive integer lower than it. Okay, and another really important thing to notice is that like 7 factorial is 7 times 6 factorial. Does everybody agree with this? So I could just break the 7 off and write the rest of it as 6 factorial. Another way of saying this is that k plus 1 factorial is k plus 1 times k factorial. So notice up here, this guy is k plus 1 factorial, which is k plus 1 times k factorial. So maybe just to keep it very clear, that's how I'm going to write it. I'll say this is k plus 1 times k factorial times k plus 1 times k factorial. On the bottom, let's look at this one first. 2k factorial. So on top I have times 2k quantity factorial, which is 2k times 2k minus 1 times 2k minus 2 times 2k minus 3, all the way down to 3 times 2 times 1. This one is 2k plus 2 times 2k plus 1 times 2k times So we could say that this is 2k plus 2 times 2k plus 1 times 2k factorial. And then I have a k factorial and a k factorial on the bottom. Now I can start just canceling a bunch of things. So there's a k factorial on the top and a k factorial on the bottom. K factorial on top, k factorial on bottom. 2k factorial on top, 2k factorial on bottom. And now let's just look and see what we have left. I still was taking the limit here. And now I have limit as k goes to infinity. On top, I still have k plus 1 times k plus 1. On bottom, I have 2k plus 2 times 2k plus 1. And what is that limit? 1/4. Very good. So the highest power of k on top and bottom is k squared. What's the coefficient of the k squared? K times k gives me 1. 2k times 2k gives me 4k squared. And so I have a 1 over a 4. So this limit is 1/4, which is significantly less than 1. And so if I do a ratio test and I get an answer that is less than 1, the ratio test tells me that the original thing, the original sum, that must converge. So I say, therefore, I have sum k going from 1 to infinity of k factorial quantity squared divided by 2k factorial converges by the ratio test. And that's it. Okay, so when you deal with these factorial type problems, you really need to understand what you mean by factorial in this, just like multiplying down. By the way, why factorial is super, super interesting. Let's see. So one thing I just like to kind of show people when I talk about factorials, the power of the factorial. So let's take something fairly insignificant. By the way, does anybody know why do we even care about factorials? Like, where do they come up? Yeah.
I think they come up in like opportunity, the way I like learned it is opportunities, I guess. So there's like 7, and then you're trying to figure out how many combinations you can have of the 7. And so like 7 factorial is the amount of like seats open against the combination. I guess.
Yeah, you're in the right ballpark for sure. So here's a simple way of thinking of factorial is, let's say I have 7 pictures and I want to hang them in a line on the wall. How many ways can I do it? Well, I take the first picture. How many places could I put it? 7. So there are 7 ways I could hang the first picture. I pick up the second picture. How many places could I put that picture? 6, because one of the places is filled by the first picture. So it's 7 times 6 is the number of ways I could hang the 2 pictures. Then how many could I add in the next one? Times 5, times 4, times 3, times 2, times 1. So that's the number of ways that you could hang 7 pictures on the wall. Okay, yeah, that is true. Where else could it come up is, well, all sorts of reasons, but anytime that you're ordering things. I had a professor tell me once that he was writing a computer program that was like for a dating game, like a dating website. And it was kind of like he was trying to write something where it would match a person up with like the person that was best for them. But the thing is, he wrote it in such a way that you had to kind of like check all combinations. But there were a lot of combinations because it's kind of like let's say there are like 7 men over here and 7 women over here. How many different ways are there to match them up? Well, the first guy you take and you say, well, which place I could put the first guy somewhere. How many places could you put him? Well, you could put him 7 places. Then you take the second guy, how many places? 6. So 7 factorial if there were 7 men and 7 women, right? Okay, this is bad in computer programming. I don't know if you know much about coding, but if you do, you know that factorials are the enemy. Why? Well, let's look at a very innocent little number. 20 factorial. Not very big in the grand scheme of the factorials that I could make up. It's not uncommon at all in coding to like have like 10,000 data points, let's say, and let's say you needed to do something where you ordered them and you had, how many ways could you do it? Well, 10,000 factorial, right? And this actually comes up in a very, very important problem in mathematics. Has anybody ever heard of the traveling salesperson problem? Nobody? Okay, that's great. It's like super important. And let's say that, so you're a salesperson, let's say that this is your home. So I'll put a little home here. And then he has to travel to a bunch of cities. And then he needs to come home. So he's going to go, and maybe he'll go here, and then 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 come home. Is that the only way that he could have made the trip? Not necessarily, assuming that there are connections between all the different cities. Well, maybe he wanted to go here, and then 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 here, right? So there's different paths that the salesman could take to hit all the cities and then come back home. This comes up now, and you might say, well, who cares about salesmen? Let them just figure it out. Well, it's not really about that so much as it is, like, maybe I say this in a different way. You've designed a machine to drill holes into a piece of metal. And I need the holes in these locations. And by the way, if you save me like 5 seconds of drilling time on every plate, we make $1 million. And it's kind of like, oh. So you mean it would be better if I took an optimal path to do the drilling? It's like, yeah, that'd be good. And so it's like, so which one's the optimal? It's like, well, let me just crank through and figure it out real quick. Well, how many holes, how many places do I have to go? How many could I go to first? 1, 2, 3, 4, 5, and 6. So there's 6 factorial ways to do this. But 6 isn't a very big number of holes to have to drill, ultimately, right? Let's say I had to drill 20 holes. Okay, so now there's 20 factorial ways that you could drill the holes. Which one's the best? And you don't want to sit down and start figuring it out, because how many possibilities are there? Does anybody have their calculator with them that can do a factorial? Okay, so this is 2.4 times 10 to the 18th power. In other words, a 2, 4 with 17 zeros behind. Okay, that's how many different ways you could get through drilling 20 holes, right? Okay, let's say, how good is the modern computer? Does anybody have any idea, like how many computations could the modern computer make in a second? Does anybody have any idea? I don't actually know off the top of my head, but let's just make something up. Like, let's say that my computer was really, really good and it could do 1 million computations each second. So it could check 1 million of these paths. I'm not sure that that's actually true, but let's say it could. So let's say it could, in each second, it could check 1 million paths. So let's divide this number by 1 million and see how many seconds it would take to do all the computations to see which is the shortest path. What would it be? So what's this number divided by 1 million? Well, 1 million is a 1 with 6 zeros, right? So it would be 2.4 times 10 to the 12th. That's how many seconds it would take to figure out that problem. Okay, how many seconds are in a minute? 60, right? So could you divide that number by 60? So minutes, what would it be? Go. What's that?
4 to the 10th.
4 to the 10th? Do you have it in scientific notation? Does anybody have that? 4.05 times 10 to the 10th. Yeah, that's it. Okay, so how many minutes in an hour? 60, right? So how many hours would it take to do this computation?
6.76 times 10 to the 8.
Okay, how many hours in a day? I guess 24. So let's divide that by 24. What would it be?
2.82 10 to the 7.
Okay, how many days in a year? 365. So what would we get? 79,000 what? 97? Oh, that seems bad.
Yeah.
How 20 factorial? If I have 20 factorial things that I need to put in an order, my computer, if it can do 1 million of the paths, check on 1 million a second, probably can't, I agree. Because it might be able to do 1 million computations, but it would take more than one computation to check a path. So I agree with you, it probably can't. But let's say it could. Then it would only take 79,000 years for your computer to finish. Doesn't that seem mildly depressing? It's kind of like, haven't we come further than this? We can't even do a traveling salesperson problem with 20 nodes. The answer is no, we cannot. Now, here's the interesting thing, is people have come up with algorithms to approximate a best path, even though they can't check it for certainty. In fact, like Amazon warehouses. Have you ever thought of being an Amazon warehouse employee? I'm guessing none of us have. But what somebody does all day is you order something on Prime and you ordered 5 things and somebody gets to go get them, right? They get to go like actually take something off the shelf, put it in a box, go find the next thing and put it in a box. Does it matter to Amazon how fast they get it done? Yes. Like we're talking, if they can get their path as short as possible to get the box filled, they might make like $1 billion extra on shortening that path because they get more boxes done quicker, right? So the traveling salesperson problem is a huge deal to these people. And they have ways of estimating a quickest path, although, and how many nodes are there in the Amazon warehouse? I don't know. I mean, a lot. I mean, maybe in the millions of nodes. And so the traveling salesperson problem in that case, like if you order 100 items, you just created a traveling salesperson problem for Amazon with 100 nodes. So 100 factorial. So no computer is going to give the optimal path to that worker, but they can maybe give them a pretty good one. And even if you could come up with an algorithm that was better for the workers of Amazon to move through their warehouse, they would pay you $1 billion, I guarantee it, for that technology. And actually, I went to a talk for a guy who was like the leading expert maybe in the world on the traveling salesperson problem. And he actually came up with a very, very good algorithm for doing that kind of work. And a little company asked him if they could use his research at their company. And then he said, oh yeah, sure, you can use it. So they took it and started using it and got intellectual property rights on it. And then Walmart bought that company for like $20 million or something, just to get the tech on that traveling salesperson problem. And that guy got nothing. It's like the saddest story ever. I was like, oh wow, that is a bummer. So anyway, the traveling salesperson problem and the idea of a factorial is a really, really, really big deal in mathematics. And if somebody could figure out a way to solve a traveling salesperson problem faster than factorial timing it, then you would be insanely rich. But it's not that easy. Anyway, so when we deal with things like this, like these numbers that we're dealing with, k factorial squared over 2k factorial, those are big numbers. And the question here is like, well, which one is bigger, faster? Is k factorial squared bigger, faster? Or is 2k factorial bigger, faster? And the answer we get is that it converges. So 2k factorial must be getting much, much bigger than k factorial squared. And if you think about that for a little while, it actually does make sense that it would be. Anyway, so all that to say, factorials are pretty cool. And they're pretty important, even when you think about something like an Amazon warehouse. They care deeply about factorial time. So, all right, that's a pretty good place to end for today. So homework over 10.6 and 10.7 is due tonight. The next section was due on Wednesday online. I changed it this morning. Now it's due on Friday. So you get until Friday to complete the next homework assignment. And then we're supposed to have an exam coming up, correct? So we will talk Friday about our third exam and get on the same page on when it will be and what it will be over. Okay, have a good day and have a good Wednesday break. I will see you on Friday.
So I submitted 10.5 and 10.7 together last week.
Okay.
You want me to switch that so I put it in together?
I would say just to be on the safe side with the grader, it's fine that it was in the last one, but you might submit it with this one too, just in case the worst happens.
Yeah.
I would say just submit it in both and it's fine. You don't have to go back and change the old one.
Okay, perfect.
Yeah.
And I did look it up. I think computers can do like 2 billion per second, but that's computations, not.
Right,
Yeah.
2 billion companies. So maybe even if it were 2 billion, like that would change the order of magnitude by 3. So maybe it could do it in like 70
Way
years.
too long.
Yeah,
Way
it's
too
not,
long.
it's not 10 minutes.
Yeah.
Yeah, by that time we should have a better order of magnitude on the computer. But there's this really famous problem that basically is, what if, alien life showed up and they, they landed on the Earth and they came out and said, "Greetings, you guys look pretty pathetic, but we've got a problem for you. If you can tell us the shortest path algorithm through all the stars of the Milky Way, we'll be back in a year. And if you do it, you get to live. If not, we'll blow up your planet." It's like the question that scientists have kind of asked is, would we live or die? And the answer is, right now, I think we would probably die. But it's an interesting problem. Yeah.
I was a little confused on how to write or to start the writing the series or sequence of this.
Okay, is this on which section?
10.7.
Okay, 27. So what they kind of want you to do is change that from the form it's in to kind of the summation form before you get started. So they've got like, it's 1 plus, is it 1/2 squared plus 1/3 cubed? Is that right?
Yes.
plus 1/4 to the fourth. Okay, so if we were to write this as a sum, we've got k going from 1 to infinity of 1 over k to the k. Does that seem reasonable? So if we plugged in 1, we get 1 over 1 to the first, which is 1. If we plug in 2, we get 1 over 2 squared, 1 over 3 cubed, and so on. So this is the closed form. And now that you see the closed form, now it's not so hard to think about like, okay, now what would I do? I think now like the root test would make it extremely easy. But the hard part is just going from there to there. Yep.